Finally, for this week, let's look at the definition and uses of independent component analysis. Unlike PCA, which is looking at the covariance of features, ICA seeks to explicitly unmix data under the assumption that what we have measured is a mixed signal of a number of independent sources. A famous toy example of this is known as the cocktail party problem. Here, the idea is that you have a number of recordings acquired simultaneously from multiple positions around a room. These recordings will capture a mixture of audio from all present. What we want is to separate out and recover the original source signals, the individual voice recordings. For example, let's play these two different mixed audio signals, taking a commonly used example downloaded in this instance from an Alto research page.
The guardians of the electronic stock market NASDAQ who have been burned by past ethics questions are moving. The guardians of the electronic stock market NASDAQ who have been burned by past ethics questions are moving.
To my ear, and perhaps yours, these sound very similar, but I assure you these are two different linear mixtures. The goal of independent component analysis is to recover the original source signals. I'll play these for you now. So a siren,
the guardians of the electronic stock market NASDAQ who have been burned by past ethics questions are moving.
And a news recording. The goal of ICA, therefore, is to learn an unmixing matrix W, which represents a set of coefficients through which we can unmix the data X in order to recover the independent source signals S. ICA therefore makes a specific assumption that the recordings at each microphone are a linear combination of source signals and coefficients A. For example, for the mixtures shown on the previous slide, we had two sources. Therefore, S, which is a function of T, is a 2 by T dimensional matrix where SIT is the sound the source I makes at the time T. We also have two microphones, which means that our mixture also ends up being 2 by T. And therefore our mixing coefficients are 2 per source and per microphone. ICA therefore seeks the inverse of the mixing matrix A, otherwise known as the unmixing matrix W, by assuming signals are both independent and non-Gaussian. Why must the signals be non-Gaussian? Well, let's assume instead that we have two Gaussian sources such that S can be represented by a bivariate unit Gaussian centered on the origin, as shown in this figure, and this is mixed with coefficients A to return X. The covariance for this distribution will return AA transpose, as S transpose is a covariance matrix with unit variance and thus is the identity matrix. What if we rotate A and assume that the data was instead mixed by the rotated A prime, returning X prime instead of X? By comparing the steps of the covariance estimation, we see that as SS transpose and RR transpose are the identity matrix, then both X and X prime have the same covariance matrix. This means that we can't differentiate between the mixtures and thus we cannot find a unique mixing matrix. If we can't find a unique A, then we can't find a unique W, and so we would not be able to recover the original sources if they were Gaussian. Accordingly, we cannot estimate independent sources with PCA, but since independence implies uncorrelatedness, many ICA methods do use PCA to pre-whiten the data such that it returns uncorrelated estimates of the independent components and transforms the required mixing matrix into an orthogonal matrix, thereby reducing the number of parameters that need to be estimated. The goal of pre-whitening, therefore, is to diagonalize and squash the data covariance matrix. In other words, rotate the data until the covariance distribution aligns with the major axes, and then use the inverse of the variance to remove all scaling. And we know from the PCA lecture that the eigenbases diagonalize the covariance matrix, and therefore by pre-multiplying or projecting the data onto U, we can decorrelate the data. We also know that the diagonal of the singular value matrix lambda gives the square of the variance, so we can normalise by dividing through by the square root. This final multiplication here by u then rotates the data back to its original orientation. Conveniently, as it turns out, optimising for non-Gaussianity has the parallel benefit of unmixing the signals due to the central limit theorem. This states that the distribution of sample means calculated from repeated sampling will tend to normality as the number of samples increases. Thus, any linear mixture x equals as will be more Gaussian than the sources, and by optimising for non-Gaussianity we can estimate our independent components. There are a variety of ways to do this, starting with estimation of kurtosis. So kurtosis is a measure of the combined weight of a distribution's tails relative to the centre of the distribution, such that a super Gaussian random variable will have a spiky probability distribution with long tails, and a sub-Gaussian variable will have a flat PDF, constant near zero, and very small for very large values. The problem with kurtosis is that it's very sensitive to outliers. Therefore, a better measure of Gaussianity is entropy, where Gaussian variables are said to have the largest entropy among all random variables of equal variance. For these reasons, the popular fast ICA algorithm therefore optimises for negative entropy. However, to do so is far from trivial and therefore outside the scope of this course. For those that are interested, details are provided in the notes. We instead will implement ICA with scikit-learn, where the fast ICA function is again found in the decomposition module, and as for our PCA, we can choose how many components we want and whether we want to pre-whiten the data, to which the answer should be true. The class has attributes including the components, which returns W, the unmixing matrix, through which we can recover the sources S, and mixing, which returns the mixing matrix A. Therefore, to fit and return the sources, you will need to apply the fit and transform function. This will apply the unmixing matrix W to X to return S. We will test this out in Tuesday's tutorial, where you will be asked to use scikit-learn to unmix the signals that we played at the beginning of this lecture. For the rest of our time, we'll instead explore a case study of how ICA is most commonly used in neuroscience, specifically for the modelling of brain functional signal from functional magnetic resonance imaging data, or fMRI. This here on the right is a video of fMRI projected onto an inflated brain surface. You can hopefully see that clusters of regions phase in and out, when yellow here represents an active region and blue deactivated ones. Note, the fMRI signal does not directly measure brain activity, but instead measures change in the magnetic properties of the brain tissues caused by changes in blood oxygenation as energy is provided to the neurons. There is a phrase in neuroscience and fMRI that what wires together fires together. In other words, any regions that are firing or yellow at any constant point in time are most likely talking to one another through neuronal connections. We can also see that there is structure in the signal, not just noise, where observation of these clusters has supported an understanding that the brain can be modelled as composed from a relatively small number of regions. For example, a model of brain regions on the surface is shown here on the bottom left, and on the right we have a network model which predicts connectivity between these regions. ICA can help us recover these regions and connections from the complex mixed signal that we record through fMRI. Here we assume that we record an fMRI signal, like the movie I showed, which shows that at each point in time, given by the rows, different brain regions are activated. For example, here, and then here, and then here, or deactivated. What we can do with spatial ICA is recover the independent sources, in other words, the non-overlapping clusters or regions, for example, here, here, and here. Where A here, the coefficients, return linear loadings which can be interpreted as the time series of activity for each brain region. This then allows us to infer the spatial location of different regions of the brain. Then we can estimate which regions are temporally correlated and thus infer that they are functionally connected. And then finally, we can use these data sources to investigate links between brain function and behaviour. Thus, the key differences between PCA and ICA are that PCA allows you to find a new linear subspace that best explains the variance in the data, whereas ICA helps when you want to find a representation of your data as independent subelements. So in layman's terms, PCA helps to compress the data and ICA helps to separate the data. Thus, in summary, independent component analysis is seeking to unmix data samples into a set of statistically independent source signals, which it achieves through factorizing a data matrix X into a linear mixture of independent sources with coefficients A. Fast ICA achieves this unmixing by optimizing for non-Gaussianity. Typically, prior to ICA, data is pre-whitened and decorrelated using PCA, making PCA an important pre-processing step of ICA. And finally, a well-known use of ICA in biomedical imaging is to separate out functional brain regions and their time courses from fMRI. So that then marks the end of the video lectures for this week on linear manifold learning. Before you finish, please complete the Keats quiz on independent component analysis.